Good evening, everyone. I welcome you all for our week 7 discussion on heat exchangers. So, this week we'll be focusing on phase change heat exchangers and condensers. Okay. So, we'll get started with defining few terms of phase change heat exchangers and a few terminology that we are going to use in today's class. So in phase change heat exchangers, we know about we can define heat exchangers now. So in these heat exchangers, when either one or both the fluids which are undergoing heat interaction, if they undergo a phase change, we call that kind of heat exchanger to be a phase change heat exchanger. So it could be a solid to liquid or vice versa, liquid to vapor or vice versa. But we are going to deal mostly on liquid to vapor phase change heat exchangers alone in this course. So we can define or we can give some examples of phase change heat exchangers now. You know about boilers in power plants where water gets converted into steam or water vapor. So there is a heat exchange, there is a phase change there, and such kind of heat exchangers we are going to call as phase change heat exchanger. And also one of the most easier examples that we see in our day-to-day life is cooling and dehumidification coil in our commercial ACs. Even there, it is a phase change heat exchanger. We'll define one more term called the pinch point. So pinch point is defined like this in a heat exchanger where the temperature difference between the two interacting streams is minimum. So if you see the figure that I present in my screen, so we have a pinch point at this location where the temperature difference between the two interacting streams is minimum. A heat exchanger can have multiple pinch points based upon the uh, kind of fluids that we are going to use. Since this is a pure fluid, we only have one pinch point here. We'll define or learn few concepts related to condensation heat transfer. So condensation happens when a hot fluid uh, comes in thermal contact with a surface which is at a lower temperature than its saturation temperature. Then the process of condensation starts. So in condensation, we have two types of heat transfer regimes, two modes of heat transfer rather. The first one is called a film condensation and the second one is called a drop wise condensation. Can someone uh, unmute and tell me in which mode of heat transfer, in which mode of condensation the heat transfer coefficient is higher?
Dropwise condensation.
Okay. Can you give me
20,
some why is it so?
20 times
Why is it so?
because it leaving free phase. It will leave the droplets will leave the free phase to the steam,
Yeah.
so that the heat transfer coefficient has been increased.
Yeah, that's perfect. So the heat transfer coefficients in uh, dropwise condensation are certainly one order higher than what we get in film condensation because as we see in dropwise condensation, the surface is such that only a part of the surface is being blocked by the liquid condensate in drop wise condensation, whereas in film wise condensation there happens coalescence of different drops happen and then it forms into a layer. So as a result, now the extent of condensation reduces in the case of film condensation when compared with drop wise condensation. So the heat transfer coefficients are certainly one order higher in drop wise condensation. uh, to study condensation heat transfer coefficients, Nusselt theory of condensation is one of the most uh, widely used for pure fluids. So he has derived equations for laminar flow heat transfer coefficient and turbulent film condensation heat transfer coefficients. So these two relations are going to be important in our class because we are going to use them in our numerical problems. So and also if we see the turbulent film condensation, we have a term called RE delta. So this is called the boundary layer thickness. So based upon the boundary layer thickness, we have different heat transfer coefficient, different formulae, numerical formulae for Reynolds number. So if Reynolds number is less than 30, we say that it falls under laminar regime, and if it is in 20 to 1800, we say that it is in transition, and more than 1800, we say that it is in turbulent. So it is good if we can remember few of these formulae. It will be at the back of our hand. So in practical condensers, the mode of condensation is mostly film wise, because for drop wise condensation, though we have higher heat transfer coefficients, the extent of or the manufacturing of such kind of tubes are going to be very difficult. So we need extremely clean surfaces to achieve uh, drop wise condensation. In most practical heat exchangers, we cannot sustain that over a long period of time. So what happens is we always fall under film wise condensation for these particular tubes. So we use mostly copper. So it falls mostly in film wise condensation regime. Uh, so in film wise condensation, if there is only one tube, as you see in this figure A, uh, the condensate just passes, drops down because of gravity. That is known. But if there, yeah, someone wants to ask something.
No,
Okay,
sir. No, sir. Sorry.
okay, fine. So as you see in figure B of the figure shown, uh, if there is only one tube and assume that we are in film condensation mode, whatever condensate, the liquid condensate that is accumulated, it just falls down due to gravity. For example, if we have a blank of tubes, that is one tube below the other as shown in C. Now C is already partially flooded with the condensate that comes from the top tube. So as a result, we cannot say that the heat transfer coefficient which we have in tube 1 is same as the heat transfer coefficient which we are going to have in tube 2, because of obvious reasons. So as a result, if we continue our discussion to n tubes, we cannot say that the nth tube has the same heat transfer coefficient as the first one, because the top surface of the second one is being flooded by the one by the liquid condensate that is formed due to tube 1. So as a result, nth tube will have a very low heat transfer coefficient. Even that was also discussed by two expressions. One is given by Kern, which gives a more conservative uh, heat transfer coefficient for film wise condensation, and more the first was given by Nusselt, theory of condensation, where we are going to do one problem on that. Uh, but more conservative relation was presented by Kern. And in this particular film condensation, we can have different regimes. Like if we have vapor which passes at a very high velocity, we can have the liquid condensate being drained away because of the velocity of the vapor. uh, and also there are different techniques to overcome uh, the depreciation in heat transfer coefficient because of this flooding. One arrangement is having a instead of having inline arrangement, we go for a staggered arrangement. So as a result, what happens is whatever liquid condensate that forms on this on the first one will not directly form, will not directly fall, will not completely flood the bottom one. So only a portion of it is flooded. So as a result, more surface area is exposed to the incoming fluid, and it aids in heat transfer. So that is one technique. Another technique which is practiced is by giving certain tilt to these condensers about 5 degrees with respect to the horizontal. More than 5 is not recommended. Between 0 to 5 they are recommended. So these are all techniques to uh, minimize the depreciation in heat transfer coefficient, or enhance the surface area that is available for condensation. So we'll get started with one of the problem. As I have told you, you can start the first one. If we have a condenser where there are 75 tubes in a vertical column, we want to know the heat transfer coefficient, the ratio of the average heat transfer coefficient to the average to the heat transfer coefficient in the first tube. I'll give you a couple of 1 minute to understand this. Obviously, you need to know the expression that I have given here, and unless you know that, we can't do. But I'll give you a few seconds to appreciate the problem. Before we do this, does anyone have any questions to ask me till this point? Okay. Okay, so let's get started with this problem. So as I have told you that there will be a depreciation in heat transfer coefficient when there are n tubes which are arranged in line because of the liquid condensate that floods the subsequent tubes. So we have 75 such tubes which are in inline arrangement. So we are interested to find out the average heat transfer coefficient of the whole heat exchanger that is found by the 75 tubes to the heat transfer coefficient in the first tube. So from Nusselt's theory of condensation, we have this formula which we need to remember, that Hn is H1 into n to the power minus 2 point minus 0.25. Okay, so we end up with once you put n value, it is just arithmetic. Once you put n value, we find that hn to h1 is 0.34. So the depreciation in heat transfer is quite huge, because the average heat transfer coefficient is just 0.35, about only 35% of what the first tube has. So we need to appreciate this fact. Any questions here?
No, sir.
Okay, fine. Let's go forward. We have a condenser where uh, water flows through the tubes with some velocity 0.5 meter per second, and steam is condensing on the outside of this surface from 80 degrees Celsius to 115 degrees Celsius. So you can neglect the wall resistance and fouling using a correlation. This we know, this is the famous Dittus-Boelter equation for cooling, which is valid for uh, fluids which don't have phase change. So we are interested to find out the average value of heat transfer coefficient. You can start working out. I'll give you a couple of minutes. Somebody's mic is on. I request you to please switch it off, unless you have some questions to ask me. Okay, we'll go step by step. So, can you find out the Reynolds number of? Uh, yeah. One more thing I forgot to pinpoint here. So we have two fluids. One is water and the other one is steam. So the first question which we need to ask here is, when the question was the average was to find out the average value of heat transfer coefficient. I need to ask a first question of which fluid. So I'm interested to find out the heat transfer coefficient of water that is flowing inside the tubes. So I'll help you out in finding this. First, find out what is Reynolds number for this water. So Reynolds number
Is
you
it
can,
is it 9281.25?
yeah, that's fine. So one of our friends says that it is around 9281. So Reynolds number we know it is defined as GD by mu, or you can write it as rho VD by mu. All other quantities are given, just we need to plug the values. Rho of water is given 990 kg per meter cube. V is given zero point 0.5 meter per second, and mu is given as 810 power minus 6 Pascal second or kg per meter second. So after finding out, if you plug in the values of these three quantities, rho v d by mu, even d is given, you can take it as 15 mm, because we have told to neglect the tube wall tube wall thickness. You can directly take the inner and outer diameter to be same. So once you plug these values, it's just arithmetic. You get a value of Reynolds number as 9281.85. Once you get that, one term in our right hand side is done. We are interested to find out the Prandtl number. Prandtl number is defined as mu Cp by K. Again, after knowing the mathematical form, it's just arithmetic now. You plug the values of mu, Cp of water, and K of water. Any answers for Prandtl number?
Is it 8.4 into 10 power minus 3?
I think you have substituted a wrong unit for Cp. It is in kilojoule.
Oh, sorry. 10 power 3.
Yeah, that was right. Prandtl number is 8.4. Once you uh, take care of the unit, the 10 power minus 3 term fades away. So Prandtl number is mu Cp by K. Mu is known. Cp is in kilojoule per kg Kelvin. So it is 4.2 into 10 cube joule per kg Kelvin. That's what we need to substitute. Uh, and K is already known. K is also given, 0.4 watt per meter Kelvin. So once you plug these values, you find that the Prandtl number is 8.4. Now you can substitute into this equation to find out the heat transfer coefficient of water. Nusselt number is defined as heat transfer coefficient H into hydraulic diameter D by K. That's the mathematical definition of Nusselt number. HD by K equals 0.023 times 9281 to the power zero point 0.8 into 8.4 to the power zero point 0.3. We are interested to find out the H in LHS.
So is it 1848 H
Yeah, that's
watt per
correct.
meter squared?
That's correct. So I'll give you 10 more seconds to work it out. Uh, After that, I'll show you the solution. Okay, fine. So we have a condenser where water is flowing in the inside of these tubes at velocity 0.5 meters per second. The dimension is given as 15 mm. So steam is undergoing condensation. It is entering at 200 degrees Celsius. Okay. So the water inlet temperature is at 80 degrees Celsius and it is leaving at 115. And we want to know the average heat transfer coefficient of water in this condition. So Reynolds number, we know it can be written as rho Vd by mu. Uh, all the values of on the RHS are already given. Rho, velocity, hydraulic diameter, that is 15 mm, and mu. Please make sure that we are dimensionally consistent. Otherwise, we should land up with the right answer of Reynolds number 9281. Okay. So the next term is to task is to find out Prandtl number. Again, it's just the mathematical definition, mu Cp by K. All the values are given, and we end up with. And one more thing, Cp was given in kilojoule per kg Kelvin. So again, we need to be dimensionally consistent there too. So we end up with Prandtl number of 8.4. So the RHS terms are all known now, Reynolds number and Prandtl number. Nusselt number is given as HD by K. We are interested to find out this term H, that is heat transfer coefficient, given the hydraulic diameter and K. So we end up with the heat transfer coefficient being 1848 watt per meter square Kelvin. Any questions here?
No, sir.
Yeah, I think this is a straightforward one. Okay, for this heat exchanger, can you find out the LMTD assuming a counterflow?
Yeah, yeah.
Maybe I'll show you the uh,
Problem.
problem.
Is it 101.49 degree?
Yeah, that's right. I'll give a few more seconds for uh, all of us to try. Okay, for finding out LMTD, we know the formula. We just have to uh, know what is theta 1 and theta 2 here. So theta 1 is nothing but 200 minus 115 degrees Celsius. Theta 2 is nothing but 280 degrees Celsius. Okay. So I'm sorry. After finding out theta 1 and theta 2, now it is just LMTD is theta 1 minus theta 2 divided by logarithm of theta 1 by theta 2. So we end up with an LMTD of 104.5 degrees Celsius. Any questions here for anyone?
No, sir.
Okay, fine. So we did this exercise for a reason, LMTD of heat exchanger. Uh, in next problem, probably we all can appreciate that uh, we only have heat transfer coefficient on tube side. If we were to have heat transfer coefficient on the other side also, uh, there are few more numerical problems that can be asked. So that we will appreciate in the next problem. If anyone has some questions, they can ask me here, or we can go forward. Okay. We have one more condenser where an organic fluid is flowing at a rate of 500 kg per minute. It has a saturation temperature of 355 Kelvin. Cooling water at 286 Kelvin is available at a flow rate of 60 kg per second. The overall heat transfer coefficient is 475 watt per meter square Kelvin. The latent heat of vaporization of this fluid is 600 kilojoule per kg. We want to find out the number of tubes that are required if 1 inch diameter, which is 2 thick, and 4.87 meter long tubes are available. 25 is about 1 inch. So you can take time. I'll give you a few minutes. Uh, After you try, I'll keep giving you little hints. It is not very different from the problem that we solved earlier. The first two steps, that is finding out LMTD, finding out, you can do an energy balance to find out TC out. Then we can do an LMTD calculation. Since we have overall heat transfer coefficient U, we can put Q is equal to UA LMTD. So U is known. So we are going to find out the number of tubes required from the term A in UA LMTD. Maybe you can try now. So the first step is to find out LMTD. To find out LMTD, we don't have one more temperature. To find out that remaining one more temperature, we are going to do an energy balance and get the unknown temperature. After finding out LMTD, we need to apply Q is equal to UA LMTD. So we'll go step by step. So can someone do an energy balance and share their answer about the exit temperature of cooling water? So it is entering at 286 Kelvin. So what is the exit temperature of cooling water?
I think it is 224 Kelvin.
224 is no, it will be more than 286
Right.
because we have uh, an organic fluid which is condensing. So water will gain heat. So definitely it will be more than 286 Kelvin.
Right.
Maybe the units are also important again. This is 500 kg per minute and this is 60 kg per second. So I'll give you one more hint. Uh, for doing energy balance, heat lost by hot fluid should be equal to the heat gained by the cold fluid. So heat is being lost by this organic vapor. Latent heat of condensation is given. So
Yeah, 356 Kelvin is it?
no, it is too high.
Hmm.
So what we are going to do is M
30.18.
yeah, it is around 32 degrees Celsius or 305.9 Kelvin. Okay, I think you people are trying. Should I give you some more time for it? Okay, those who have got 305.92 Kelvin, you can go ahead and calculate the LMTD. Any answers for LMTD?
Is it 31.38?
No, it is around 58.
LMTD is 59 and tube requires are 470.
Okay. we have one answer. Our friend, one of our friends says it is 470. Okay. Uh, I'll show you the solution. So, as I've told you that we are interested to find out the exit temperature of cooling water which was entering at 286 Kelvin, because I'm interested to find out LMTD, the sole purpose of finding out the temperature. So, while one fluid was undergoing phase change, so while we apply energy balance equation, so we have m dot of the organic fluid into HFG of this organic fluid, that is latent heat of vapor condensation, that equals m dot Cp of cooling water times delta T of water. So m dot Og is given as 500 kg per minute, that we are going to convert into seconds, and HFG of organic fluid is also given. M dot of cooling water is also provided. Cp is about taken in SI unit, 4180 joule per kg Kelvin, and we are interested to find out this parameter Tc out. So once we plug the values, we get a value of 305.9 Kelvin or 32 degrees Celsius. Okay, after we find out the exit temperature of water, we are interested to find out the LMTD. So theta 1 becomes Th1 Th in minus Tc out, and theta 2 becomes Th out minus Tc in. So once we find out theta 1 and theta 2 values as 49 and 69 respectively, the LMTD comes out to be 58.5 degrees Celsius. We know this formula uh, from day 1. So we get an LMTD of 58.5 degrees Celsius. Is everyone clear till this point? Okay, fine. So next up we are trying for heat transfer calculations. So Q dot, or the heat load on this heat exchanger, can be written as m dot of this organic fluid into latent heat of condensation, that equals UA LMTD. So LMTD is known 58.5 degrees Celsius. U is given in our question as 475. LHS is already known, that is heat load on the heat exchanger. So as I have told you that we are interested in finding out this parameter A. A is nothing but the heat transfer coefficient, heat transfer surface area. So that is written as pi dl times number of tubes. Pi dl is the surface heat transfer surface area per tube multiplied with number of tubes n. So n comes out to be 470. Any questions here?
No, sir.
Okay. So as I have pointed out that in the previous question, if we were to have an overall heat transfer coefficient instead of per side heat transfer coefficient as we had in previous question, we could have done a similar exercise even for that geometry too. Okay. If no one has any other questions, we can jump to the next one. Okay. So for the same question, I am interested to know the number of tube passes if the water velocity is to be kept under 2 meters per second. I have a restriction on cooling water velocity. So how many tube passes should I take for this condenser if the water velocity is kept uh, to a minimum of 2 meters per second, to a maximum of 2 meters per second? You can take hint from what I wrote here.
Hello.
Yeah,
Can you please go back to the statement
okay.
slide?
This one,
Is density given?
uh,
Density of water,
you can
or
take
we
it.
have to assume?
You can take it as 1000 kg per meter cube if you want.
Okay, and okay. Inside, I think this thickness is required
Yeah, thickness is
find-
already given, 2
uh,
mm thick,
to
and it
find
is
out.
25 mm OD.
Yes, yes. Thank you.
Yeah, you can take the density of water as 1000 kg per meter cube. That's a fair value. So has anyone got answer for number of tubes per pass? I think we should be able to find out NP from this. M dot C is known, 60 kg per second. Rho, we are going to take it as 10 cube kg per meter square meter cube. uh, m dot can be written as rho av basically. So rho times area of cross section into velocity. Velocity is known, it shouldn't cross 2 meter per second. Any answers? Okay, so I'll denote m dot c as the cooling water mass flow rate in each pass. Okay, so in each pass, I have NP number of tubes. So NP times rho AV will be the mass flow rate per pass. Okay, so we know rho, this pi by 4 d square is also known. Di is, we are going to take the cross sectional area because not the heat transfer area. This is the continuity, this is from the continuity equation, m dot equals rho AV, that is a constant. Okay, so Di, which is nothing but uh, 25 mm minus 2 times 2 mm, so it comes out to be 21 mm is the hydraulic diameter that is available for cooling water to pass. So 21 mm should be taken here, pi by 4 times 21 square in mm squared times velocity of water. So we get number of tubes per pass as 86.61. Okay, so once we get number of tubes per pass, it will be just the division. Now we have the total number of tubes as 470 that we calculated in the previous question. It will be 470 by number of tubes in each pass. So we need a 5 pass heat exchanger for making the cooling water not to exceed 2 meters per second. Any questions here? Okay, if there are no further questions, I'll give you one more numerical to work out.
Hello.
Yeah.
Uh, in this problem,
Mm.
just want to know, can you draw a schematic diagram of how the passes will be arranged?
You can have an arrangement like this if, uh, for example, if I take a shell and tube heat exchanger,
Mm-hmm.
I assume that my tube side entry is in this fashion.
Okay.
So I divide this will be my first pass. Uh, I'm not drawing the complete cross sectional area of tube. I'm just drawing a
Okay.
streamline of it. Okay,
Yes.
a streamline of the uh,
Yes.
water particle that I'm following. Okay, this will be my first pass.
Okay.
This will be my second pass. So this will be my third pass, and so on, and it will go out in go out from this. Okay,
Okay.
so
Okay.
I have 5 such passes. This will be
Mm.
my first pass, second, third, fourth, and fifth.
Okay. So
Okay, in
i-
each
is it
pass, again I have uh, 86 number of tubes in each pass. So this
Okay.
is going to get divided into 86 tubes, and those 86 tubes are going to run for 5 passes.
Mhm. So number of passes is like number of turns the fluid is
Yes,
taking.
yes.
Okay, thank you.
Yeah.
We can move on to next question.
Okay. Any other questions here for anyone else?
No, sir, no, sir.
Okay, fine. We have one more question. I think this should be an easy one. Here is a question where we have two different heat transfer coefficients rather than the question being specifically giving the overall heat transfer coefficient. Only that is the change here. We have two different heat transfer coefficients. We will be required to find out the overall heat transfer coefficient and then proceed further. So I think you should be quickly able to do this. We have a steam condenser which has 3000 tubes of 20 diameter each. Cooling water is entering at 20 degrees Celsius with certain mass flow rate. The heat transfer coefficient on tube side is given, and also on the shell side is given as 1500 and 15,500 watt per meter square Kelvin. Uh, the steam condenses at 50 degrees Celsius, and the heat exchanger heat load is 230 megawatt. Assuming that the latent heat of steam is 2380 kilojoule per kg, and assume a counterflow arrangement, I want to know the tube length per pass if two tube passes are required. It is not different from what we did from the previous two problems, just that we need to now calculate overall heat transfer coefficient. So can you first find out the overall heat transfer coefficient? You can take 1 by UA as 1 by HIAI plus 1 by HOAO. And one more important assumption you need to make is you can neglect the wall thickness. So as a result, what happens is you can write
Involved.
yeah, it's a thin wall tube. So you can directly write 1 by U as 1 by HI, 1 by HI plus 1 by HO.
Is it 6,526?
Yeah, that's correct. Yeah, it is a thin walled tube. That's the assumption that we are going to make because we don't know the geometry. So if we neglect the wall thickness, we can write 1 by U as 1 by HI plus 1 by HO. So once we plug the values, we get an overall heat transfer coefficient of 6525 watt per meter square Kelvin. Uh, Once we get this, we are interested to know the exit temperature of water again. Why? Because we are interested to find out LMTD. Why? Because we are interested to find out A. So again we are going to do an energy balance. The condenser heat load is already given as 230 megawatt. So that 230 megawatt equals m dot Cp delta T of water. We know m dot of water. Cp we are also going to assume as 4180 joule per kg Kelvin. It is entering at 20. We want to know the exit temperature.
Is it 38.25 degrees Celsius?
Yeah, that is fine. So I'll quickly go through the solution. Uh, Again, we know the heat load on the heat exchanger as 230 megawatt. That equals m dot Cp times delta T of water. So m dot is given as 3000 kg per meter cube. Cp we are going to assume as 4180 joule per kg Kelvin. Inlet temperature is known, and the exit temperature, once we plug in these values, we get as 38.31 degrees Celsius. After finding this out, we are interested to find out the LMTD. Yeah, go ahead and calculate what LMTD this heat exchanger has. Any answers for LMTD?
Nine is 19.46.
Okay, I'll give a few more seconds for others also to find out. People who have found out LMTD as 90, around 19, they can go ahead and calculate the tube length. You can now write Q dot as UA LMTD. Now you have all the uh, parameters except for A, heat transfer area. Uh, okay, so LMTD is again found out like this: TH in minus TC out. That comes out to be 11.69, and at the other end, theta, that is TH exit minus T cold in, that comes out to be 30 degrees Celsius. So once you plug these values in the definition of LMTD, we get 19.43 degrees Celsius. So after we find out uh, the LMTD, we are going to use this in this equation Q dot equals UA LMTD. We found out U, and then we are interested to find out the length. We already know the LMTD. So we are going to play with L now. We are going to play with A now. So that is nothing but pi d L times number of passes into number of tubes. So we have 3000 tubes that is accommodated here. We have two passes that is already mentioned, that we need to find out length of that heat exchanger when two passes are required. So even that is accommodated here. And pi dl is basically the heat transfer area per tube, that multiplied with LMTD 19.43. So length comes out to be 4.8 meters. Any questions here? Per pass we need around 4.8 meters when two tube passes are required. Any questions here?
No, sir. No, sir. Yeah,
No.
it's clear.
Okay, fine. I just want to add one point here. One of our friend was asking if uh, number of passes is equal to number of turns. No, for understanding purpose it was like that, but we need to count upon this one. This is the first pass. This is my second pass. This is my third. This is my fourth, and the exit was fifth. Okay, for understanding maybe it was like that, it is equal to number of turns, but no, while saying that we have 86 tubes in one pass, so this is going to be my first pass, then it takes a turn, then it becomes my second. All 86 tubes are running around for 5 passes. Am I clear?
Yes, sir.
Okay, fine.
Yeah, clear, sir. Clear.
I think we'll take up this problem
So,
in the next session. Uh,
Hello, sir.
yeah,
Uh,
sir, one more request,
are we
sir.
stopping now or?
yeah, we are going to stop.
Sir, is
Uh,
it possible to conduct one request, please?
Yeah,
Is it possible to conduct the class between 3 to 4 p.m., sir? In the
no,
next session?
no, it is already scheduled by NPTEL, so we cannot reschedule it. Yeah,
Sir, examination fill in the blanks will be also there, only four choice question.
that will be communicated to you, the pattern of exam.
Okay, sir. And
Okay.
when will be uploading this period lecture because I joined late today.
This I'll be uploading it by today evening, maybe in a
Good.
couple of hours in my in
But
the
then, sir,
YouTube.
YouTube only 3 4 is initially was uploaded. Afterwards, it is not there.
No,
YouTube, sir.
in my
Channel.
in the channel that was given,
Yeah.
even 5 and 6 are also uploaded.
No. Sorry. Okay.
Yeah.
Okay. Thank you, sir.
Okay. Uh,
Hello.
yeah.
Can I ask you a question?
Hello,
Yeah.
sir.
Sure.
Okay.
Hello.
Yeah. Sure. You can go ahead.
Can you take your slide to question number 2 that we solved today?
This one.
This one. Yes. In this, we found out the heat transfer coefficient
Yeah.
for the two-side fluid using this. Okay.
Yeah.
I have gone through the latest assignment number 7. There
Okay.
also we have the same type of a problem.
Okay.
Only I think values are changed.
Okay.
Uh, so in the same continuation with with the problem, there is a third question
Mm-hmm.
where we have to find out the number of uh, I think tube length.
Okay.
So to find that tube length, we require to find the value of u,
Yeah.
and steam side no data is given here for
Mm.
heat transfer coefficient.
Yeah.
So how to proceed for that?
The heat transfer coefficient, you can take the overall heat transfer coefficient, you can take it as 1848.35.
But this is water side, no, or tube side.
Yeah, this is tube side. When I have gone through, when is the last date for the submission?
Submission, I think next Wednesday coming. I think
14, sir, 14.
14th.
14, 14.
So we don't have one more class for it, right? Mm, I haven't gone through that.
14th of September.
Okay, I haven't gone through that, but let me go through that, and only then I'll be able to answer you.
Okay,
Okay?
please, if it is possible from your side,
Yeah,
please correct it as soon
yeah,
as, because without the steam side data, we are not in position to find U factor, and without that we cannot find area.
yeah.
So
Let me go through that question. Yeah,
please to take your
let
time
me go.
and by tomorrow or so, correct, correct it.
Hmm.
Sir, I had one more question
Mm-hmm.
regarding the last assignment, assignment number 6.
Mm-hmm.
Uh, there was I had put up this issue on the forum also.
Okay.
Yes, sir.
I haven't got any reply for that.
Hmm.
That was regarding the question number 1 to 7. It was a common data problem
Okay.
regarding plate and fin type heat exchanger. First three were where there was not any issue. Only the geometrical parameters were there. But I've also gone through the solutions you have provided.
Hmm.
I think yesterday only it was released.
Mm-hmm.
So there is a little discrepancy that in the question itself, in the original assignment,
Hmm.
the data was missing regarding the flow rate or velocity or so. But in assignment, in the solutions you have published, that data is there, and based on using that data only, the remaining questions could have been solved.
Okay.
So,
So
hmm,
some part of data was missing for which question in particular?
question number 1 to 7.
Yeah, yeah. 1 to 3 was fine. That's what you told, right?
Yes, yes. 4, 5, 6, 7.
4, 5, 6, and 7.
Uh,
Okay, I'll take up this matter too.
mhm.
Yeah,
Uh,
Okay.
Please go through the
yeah.
all
I'll
the
take it
matters
up.
that we have put up on the.
Mass flow rate we are not given.
Yes,
Sorry.
yes.
Mass flow rate of gas
Yeah, yeah.
and
I'll take it up, and I'll ask professors to have a look once if the
Hmm.
mass flow rate is not given. Right.
And also consider it for the evaluation purpose.
Yeah, I'll put a word to our professors regarding this issue.
Hmm.
Yeah.
Okay, sir. One more thing
Mm.
regarding the exam. We have gone through all the matter, all the content, and all the lectures. It is quite a complex topic,
Mm.
and the correlations are also very tough
Yes.
to tough to remember.
Yeah.
So, so how to?
The basic ones we have to remember,
Hmm.
but if there are two complex correlations, that will be provided.
That those will be provided.
Yes. If
Okay.
you go through the questions, some of
Hmm.
the correlations they are already provided in the question,
Hmm.
uh, but some basic correlations we have to remember.
Okay. And one more thing, for study purpose, whatever lecture slides you have provided, that will be sufficient, or because the references you have provided, those are very huge.
You can take the study material which is given in the class.
Mhm.
If you want some more questions, you can refer to the textbooks there.
Yes, the references are there, like R.K. Shah and
Yeah,
Case and London book is there, but those are
yeah, they are
very
very
vast one.
comprehensive because the topic itself, heat exchanger topic itself, is a
Yes.
vast one.
Okay, so
So
So the questions will be manageable one, no?
Yes, yes, yes,
Otherwise, it will be very tough to crack this exam.
yes. It will be manageable once you follow the lectures and assignment problems.
Okay, okay,
Yeah,
okay. Thank you, thank you, thank you. Have a nice day.
yeah. Any other questions?
No, sir. Thank you, sir.
Okay, we'll end the session here then.